Hey guys, Ms. Gosling here. Now, in this video, you're going to learn about waves in motion, or more specifically about wave behavior. So by the end of this video, you'll be able to describe what happens when waves interact with physical media. And of course, when I say describe, I mean describe it quantitatively. So let's go ahead and get started. So I want to start by talking about ray diagrams, because ray diagrams are a really useful way to express what happens with a wave, and specifically to express the motion of the wave. So say we have a wave kind of traveling straight to the right like so. So this is the velocity of the wave. So our wave fronts we're going to represent by lines. And those are just each kind of the beginning of each new wave. So the closer lines are together, the shorter the wavelength, the farther they are apart, the longer the wavelength. Now, our ray diagram is going to be exactly perpendicular to our wave fronts. So it's going to show the direction of the motion of our wave. So again, the ray diagram is how we show the direction of the motion of our wave. So they are always going to show the direction of the wave's propagation, and they're always going to be perpendicular to my wave fronts. So you can see here one example of a ray diagram. This one for a beam of light that is being reflected, or any wave really that's being reflected. So our wave fronts are these black lines, and the ray diagram is showing the direction of their motion as they are reflected off of this surface. Now, one thing that's really important to know about reflection is that our angle of reflection, our incident angle, so the angle of our incident wavefront, is equal to the angle that our wavefront is going to be reflected at. And when I say angle, what I mean is the angle from a line that is perpendicular to our surface, so from the normal of our surface. So again, I want to draw my ray diagrams so that their angle is the same for our incident wave and our reflected wave. And you can see that equation here on the right. And again, a key takeaway, we're looking at the angle between the normal and our ray, not between the ray and the ground. So this is not the angle I'm talking about. So reflection is something you've probably all seen in things like mirrors, ponds, and you've also probably heard it as well if you've ever been to an auditorium with nice acoustics, or if you're somebody who likes to sing in the shower. Another thing that you've definitely seen before is something called refraction. And a really good example of refraction is looking at a pencil in a glass of water. So we have our water like this, and I've got a pencil kind of sitting in it, like so. What I'll notice is that in the water, the pencil is going to look as though it's been bent. So rather than continuing to look like a straight pencil, even though we know that, of course, the pencil is not actually being bent by the water, the image of the pencil is going to bend. And this is something called refraction. So refraction is best defined as the bending of a wave as it changes mediums. So on the left here, we have a picture of a wave going through refraction. So right here, this straight line is the boundary between air and glass. Our wave is starting in air and then traveling into glass. And you can see that my wave is bending once it touches that glass. Here are my wave fronts, of course. And you can see here is my ray diagram. So the first thing we want to look at is the angle, again, between the normal, again, that line perpendicular to my surface, and my wave, my ray diagram, my direction of propagation. So if we call this theta 1 and this theta 2, what we'll actually find is that the sine of those angles, so the sine of theta 1 divided by the sine of theta 2 is equal to the index of refraction for glass, so for my second medium, divided by the index of refraction for my first medium, or more clearly, n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. Now, this n1 here and N2 as well, both refer to my index of refraction. So this is kind of similar to the spring constant, in that it's something that is a quality of the medium versus something that we can measure. Or so we can measure it and we can calculate it, but it's something that is a quality of our medium. So it defines kind of how quickly our waves can travel in that medium. Now, there's one thing that I want to add here. So we can see that my waves are closer together, which means that they have a shorter wavelength. What that also means, they are closer together in glass than in air, which means they have a shorter wavelength in glass than in air. What this means is that their speed is also going to change as the wave goes from glass to air. So I'm going to add here that its velocity in the first medium over its velocity in the second medium is also equal to N2 over N1, or the sine of each angle. So these are going to be my key equations to help understand refraction. And in fact, these equations are often written more simply with the printed equation here, which is known as Snell's law. Now, one thing I want to clarify, when light enters a new medium, some of it will likely be reflected and some will be refracted. So in most situations, a more accurate version of my ray diagram would have some of my light going into the glass, but some of it continuing to be reflected at that reflection angle, so at that same angle that it went hit that barrier at. So let's talk about one situation where all of our light is reflected instead of refracted.